Okay, let's look at a different example of how the difference of squares can look. When we focus on the word squares as being x squared, that's kind of a misnomer. What this is saying is that you have two terms, right? First of all, it has to be a binomial, right? We've got two terms. They have to be subtracted, right? So we're looking here, that's the difference part. The squares part implies that I can get, or I can produce this number by multiplying something by itself, okay? Now, we typically call that a perfect square, right? So the 16 is easy because we can get 16 by doing 4 times 4. Now, the x to the fourth in this case, right? This is still a perfect square. And the reason is because I can multiply x squared times x squared and get x to the fourth. So this exponent does not have to be a 2 in order for this to be a perfect square. But I have to be able to produce this term by multiplying something by itself, because that's what squaring is. Okay, and the rule of thumb here is if this is an even exponent, you're always going to have a perfect square. Okay, so for example, x to the sixth, if you remember your exponent rules, that's x cubed times x cubed, because when we multiply exponential terms, we add the exponents, provided the bases are the same, right? So x cubed times x cubed is x to the sixth, because 3 plus 3 is 6. Anytime we have an even degree, an even exponent, that is a perfect square, okay? We're always going to be able to cut that number in half. Any number that can be cut in half into identical numbers. Okay, so in this case, this is a perfect square. So is this, and I can factor this into binomials. We take one of these, we put it here. We take the other one, we put it here. We put one of the fours here. We put one of the fours here. One of these binomials gets the plus, one of them gets the minus, right? That's the curveball here. One gets a plus, one gets a minus. This is where we get the term conjugates. I'm just going to keep writing it, okay, because it's going to get used in a couple of different instances. So the product of these two conjugates is the difference of these squares, okay? Now, in a case like this where the exponent starts as something more than 2, you got to be careful because we have even degrees here. Each one of these binomials, okay, here and here, has perfect squares in them. Now, this is what we call the sum of squares, right? Because it's a plus sign. We'll talk more about that later on. That's a totally different universe of numbers called complex numbers, and we'll talk about that when we need to. Right now, this is the difference of squares. We've still got a minus sign here, okay? And x squared is x times x, and 4 is 2 times 2. So if I want to factor this expression completely, there's nothing that I can do with the sum of squares, okay? The sum of squares does not follow the same rules as what we're doing right now. It will when we start talking about complex numbers, but that's not the case. But the difference of squares here can still be factored even further. Like if you think about the problems that we did here, both of these had squareds in them, okay? So that's, we're in the middle of this problem, and we have a squared term minus a squared term. So I can take the x's and put them here. I can take the 2's, put them here, one with the plus, one with the minus. Now, again, we have a difference here in this binomial, but this is no longer a perfect square anymore. So if we wanted to factor this expression completely, we'd have to bring it all the way down to here. Okay, so rule of thumb, if the exponent is even, it has a perfect square root. We can write it as the product of these exponential terms, or these exponential terms where each one of these is half of that number, right? So the 4 became x squared times x squared, right? This x squared became x times x, right? Which is really x to the first and x to the first. So anytime this is an even number, we're calling that a perfect square, okay? So we have a binomial with a difference, and each of these is a perfect square. We factored into conjugates. One of the conjugates here was also a difference of squares that we factored even further to look like this, okay?